Hello, networking nerds. Welcome back to my channel. So in this video, I'm going to be doing STP lab. So it's going to be a complete hands-on lab where I'll be doing a lot of stuff. So if you're looking for concept or if you're looking for just a theory, you can read my blog. I have recently published a blog on STP. So I have attached the link in the description. So you can read the blog to understand the basics. So I'm not going to talk about the basic stuff here, the very basic stuff. I'll be doing a complete hands-on lab. So this is my lab setup. So this video might be a little longer. So please be patient and finish the video because I'm going to be doing a lot of stuff. So it will be very helpful for you to understand spanning tree, how actually spanning tree works in a real network. Okay, so this is my lab setup. I have three switches, one spine, two leaves, and if you look at the priority, all the switches have the same default priority, and the MAC address is also. And I have a server connected to dual homed to both leaves, and I'm using different VLANs. So, and this is not an actual server; it's an Arista EOS. I'm just using it as a server because at the end of the video, I'll be doing a lot of failover scenarios. I'll be shutting down some interfaces. So I'll be analyzing the STP convergence, okay, by shutting down certain interfaces. So how the MAC address table are updating and how the spanning tree is converging. So we'll be doing that testing using this server. I have configured a gateway on the spine. So I'll be doing continuous ping from the server to the spine, and I'll be doing the failover scenario, all these stuff later in the last part of the video. So and this setup is in triangle shape, as you can see, and all the links have the same cost, which is 20,000 because it's a virtual lab. I'm using Arista CEOS on a container lab, so all the path, all the links have the same cost. So without any delay, I'm going to get into the lab. Okay, so I have three switches, as you can see. On the left I have leaf 1, middle I have spine, and on the right I have leaf 2. Okay, let me show you the spanning tree. So you can just take a screenshot of this topology because I'll be going back and forth between CLI and this topology to explain it. But still, it would be better if you have this topology in a different screen, so it will be easy for you to follow up. So now, show spanning tree. You can see the spine is not the root. So right now, let me go back to the topology. Right now, all the spines have the same priority. So the next deciding factor is the MAC address, and leaf 1 has the lowest MAC address among the three switches. So leaf 1 is expected to be the root bridge of this setup. So servers don't participate in spanning tree, so we don't have to worry about it. So spine 2 show spanning tree. Okay, we can clearly see that who's the root here based on the interfaces 81 and 83. Yeah, it's definitely leaf 1. Yes, as expected. Right now, in a default configuration, I did not change any configurations. I just brought up the lab, and the spanning tree is by default enabled on all the switches. So right now I'm using Arista CEOS lab. So as you can see, spanning tree is enabled by default. So on all the switches, if the switch is an L2 switch, if the if, if the switch is an L2 switch, then spanning tree will be running by default. So in a default, I can see leaf 1 is the root bridge of this setup, the fabric. The reason is because between in the election, the first deciding factor is the bridge ID. So since all three switches have the same bridge ID, or we can say priority, because why I'm not saying priority is that because the bridge ID is a combination of priority sys ID here. So sys ID is, we can say that the first two digit of the MAC address, and I can see the last ext0. That ext0 is the MST0, that MST instance. Right now, the switches are running MSTP. So by default, Arista, supports MSTP. So we'll be also configuring RSTP as well as rapid PVST later part of the video. So we'll be seeing that there in the rapid PVST, we'll be seeing different bridge IDs, because it will be priority plus SysID plus VLAN ID, because each instance will have its own instance ID, which is basically the VLAN ID. So we'll be having different bridge ID for different instance. So we'll be seeing that in the rapid PVST, but rapid PVST I'm not going to talk about much, because we'll be only focusing on how spanning tree actually converges, how it behaves when a link goes down, how the election happens, for example, root bridge election, root port election, and how an interface becomes designated, why an interface becomes alternative. So all these things we'll be seeing it on the CLI. I'm not just going to talk about it. We'll be seeing it on the CLI live. Okay. So the first use case, because right now Leaf 1 became the root bridge because it has the lowest MAC address. So the first use case, so I have about eight use cases. I have listed these use cases in my blog. So you can go to my blog and read the use cases, because I don't want to waste my time listing all the use cases here. So I'll be going over one use case after other. So first use case is I'm configuring the spine as the root bridge, or any switch as the root bridge. Okay. So right now in default, because we don't want the default spanning tree, because we want in an actual network, a network engineer wants a particular switch to be the root bridge of the network. It's usually the spine or the core. Okay, so what I'm going to do is, now I'm going to configure the spine as the root bridge of the network. So since I'm going to do that by changing the priority, or I can say the bridge ID, because if I change the priority, it will change the bridge ID. So I can say that I'm going to change the bridge ID by changing the priority. Okay, so I can say spanning tree priority. This is one way to do it. So I can configure a priority. The lowest priority that I can configure is 0, and the highest priority I can configure is 61,440. And the bridge priority is then increments of 4,096. So I cannot configure any number between 0 and 61,000. It has to be increment of 4,096. So, but Arista has other options as well. You can basically configure the priority, 0 priority. So let me do that by configuring 0 priority. Before doing that, let's watch how spanning tree converges in live. So I'm giving this cool command. Watch if, let's say, show spanning tree. So now I'm going to configure this as the priority as 0 on the spine. So now look carefully. Okay, now you can see the output on leaf 1 and 2 has changed. Right now, the spine is the spanning tree root. So spanning tree now shows that spine is the root bridge because it has the lowest priority among the three. Okay, but you have to look clear, look at this carefully, because I'm going to be doing some other configurations where we'll be doing this priority 0 as well, but it will be different. So just look at the difference here. If you look at the priority, it's 0, but the MAC address is the same MAC address. It's the switch's MAC address. Okay. So we'll be also doing one more command where we'll be seeing a different MAC address. Okay. So I configured this as I changed the priority. Okay. Configure the priority to 0. So this happened. Okay. Spine became the root bridge. So let me remove this configuration. Okay, now everything has returned to the default. So now what I'm going to do is spanning tree root. There are some other options as well in Arista. So there are three options. One is primary root, secondary root, and super root. So I can configure a switch as either as a primary root or secondary root or as a super root. So we'll be seeing the difference between all three. Okay. So first I'm going to configure it as a secondary. Okay, I configured now spanning tree converges. Watch out for leaf 1 and 2, because whatever I'm doing here, whenever I make as a config, whenever I do a configuration on the spine, the spanning tree will converge on both leaves. Okay, so now if you look at the spanning tree, if you look at the spanning tree, if you look at the right now, I configured the spine as a secondary root. Secondary root. So if you look here, spine is the root bridge, because if you compare the bridge IDs of all three switches, spine has the lowest bridge ID. Okay, and if you look at the number, the priority, it's 16,000, 16,384. Okay, so if I configure the a switch as a secondary, the priority would be 16,384. Okay, okay, but still it is lower. It is the lowest among the three. Let's say some other switch has lower than 16,000, because 16,000 is it's not the lowest. So what I'm going to do is I'm going to configure the now spine as the primary. Okay, primary I'm going to configure on the spine now. Watch out for the difference on the leaves. Okay, okay, primary now. So spanning tree. Now the spine is still the root, because still if you compare the bridge ID of all three switches, spine still has the lowest or lower bridge ID. So now if you look at the bridge ID, it's 8,000. So when I configured this spine as the secondary, the bridge ID was 16,000 something. Now I configure the spine as the primary, so and the priority is 8,000 something. Okay, let's say 8192. Okay, so now what I'm going to do is I'm going to configure spanning tree root super. Now spanning tree, it's not converging, but there are small difference in the root section. Show spanning tree. And if you look here, the spine is still the root, but if you look at the priority, priority is 0, and there is one subtle difference, which is the MAC address. If you look at the MAC address, it's 0, 1. This is the lowest MAC address possible. So right now, the spine has the lowest priority as well as lowest MAC address. If you remember, when I configured the spanning tree priority 0, the MAC address was the original MAC address of the switch. But when now I configured the spine as the super root. Now the priority is 0, and the MAC address is also the lowest MAC address, which means I'm saying spine is saying that, hey guys, I am the root of this fabric. I am the root of this L2 network. Nobody else can become root, because I am the root, because I have the lowest priority and lowest MAC address, because the MAC address is unique per device. So nobody else in the network can have this MAC address unless somebody else configured spanning tree super root on that switch as well. But configuration errors, it's a human error, so we cannot blame spanning tree for that. So now I'm going to keep the spine as the root bridge of this network. Okay, so I'm not going to change anything on the spine now, so I'm going to leave it. So I'm going to keep spine as the super root of this network. Okay, so next, this is the use case 1. Use case 1 is completed. Test case, let's say test case 1 is completed. So on the test case 2, what I'm going to do is I'm going to be focusing on root port election, or we can say selection. Okay, so how the root port is elected, why a particular port, and what are the factors, what are the, let's say, what are the values that have been taken into account when electing the root port, that we will be seeing it. So right now spine is the root bridge, so all the interfaces on the spine becomes the designated port. So it's a designated port. So we are not going to focus on the spine, because spine doesn't have any root port, because spine is a root bridge. So next, I'm gonna let me explain why how the root port election right now is happening. If you look at this, so the root port election happens based on the root path cost. So whichever port has the lowest root path cost will become the root port. If there is a tie-up, if let's say if multiple interfaces have the same port or same root path cost, then the next deciding factor would be the port ID. So the lowest, whichever interface receives the lowest port ID. I'm saying whichever interface receives, not has. Whichever interface receives the lowest port ID will become the root port. So we will be seeing both as well. I'm going to be changing the path cost as well as I'm going to be changing the port ID. So we'll be seeing both uh, test cases. Okay, both scenarios. So first explain how the default setting is now. So right now, if you look at the from let's say on right now the spine is the root bridge. So leaf 1 and 2, they have to select a root port. So every switch, every non-root bridge, let's say every non-root bridge must have a root port. So that is the rule. It is going to be one per switch, one root port per switch, because if I have two root ports, then that will create a loop. So every switch must have one root port. So the root port will be the best path or best port to reach the spine. We can say that the best path. It is the best path to reach the spine. So how the best path is calculated? It's based on the cost. It's very similar to OSPF, like how the shortest path is calculated. So that is an advanced level for STP, to compare STP with OSPF. So I'm not going to do that. So here the best path is based on the path cost. If you look if you look at the leaf 1 has 3 paths to reach the root bridge, which is the spine. So path 1 is this, and the total cost is 20,000. And path 2 is this, and the total path is 20 plus 20, 40,000. And the third path is this, and the cost again is 40,000. So ET1 has the lowest path cost, so ET1 became the root port. On leaf 2 as well is the same. ET1 on leaf 2 has the lowest cost to reach the root bridge, so it has become the root port. So this is the default behavior. Okay. So what I can do is I can manipulate this. So what I'm going to do is now right now ET1 is the root port. Now I'm going to make ET3 as the root port. Right now ET3 has path cost of 40,000 and ET4 as well as the path cost of 40,000. So ET1, I'm going to configure the path cost higher than 40,000. So I'm going to configure the path cost of 50,000 on ET1, so that in the election ET1 will lose to ET3 and 4. Okay. So anyway, we'll be seeing that. Okay. Let me go back to the topology. So I'm gonna say watch if. Okay, so let me go to leaf 1, interface Ethernet 1. So right now the cost of Ethernet 1 is 20,000. You can see it here. I'm gonna say spanning tree cost. I can the the lowest cost is 1, and the highest cost is too many zeros. So let it be. So so the highest cost is 2 multiple zeros. So now I'm gonna configure, because ET3 and 4 have the cost of 40,000. So ET1, I have to configure higher. So I'm gonna configure 50,000. So now you can see here on leaf 2, it has changed. If you look at ET3 and 4 has become designated. So we'll be seeing that. So now source spanning tree. Now if you look carefully here, now ET3 has become the root port, because ET1 has higher cost to reach the root bridge, which is 50,000. So ED3 has become the root port because it has lower lower cost path cost root path cost than ET1. So you might be asking this question. Okay, you are saying ET3 has lower path cost than ET1, so it's become the root port. Then what about ET4? ET4 also has the same root path cost, which is 40,000. So ET3 and 4 have the same root path cost. Then why ET3 is the root port, not ET4? That is a good question. Okay, so let me explain that as well. So right now ET3 on leaf 1 is connected to ET3 on leaf 2. ET4 on leaf 1 is connected to Ethernet 4 on leaf 2. Okay, so if you look at let's focus on leaf 2. Okay, leaf 2 ET3, if you compare the priority, let's only look at the priority. Okay, if you compare the priority is lower than ET4, which is 128 is the priority. It's a priority 128 plus the interface ID. So if ET3, that will be 128.3, ET4 128.4. That 128 value is default. So ET3 has the lowest port ID. ET4 has, I would say, ET3 has lower port ID than ET4. So what is happening right now is, let me go back to the topology. So right now, from ET3, this leaf to ET3 is sending a port ID to ET3, and ET4 is also sending a port ID to ET4. So now, if we compare these two, ET3 is winning because ET3 is receiving lower port priority than ET4. 128.3 is lower than 128.4. So ET3 has won won the election because it is receiving lower port ID, I would say, port ID from the neighbor, okay, which is leaf 2. That's why ET3 is the root port. So what I'm gonna do is now I'm gonna make, because if you don't, because we want to see that on the CLI. Just okay, I explained that this is what is happening, but I know you want to see that on the CLI, even I want to see that on the CLI. So what I'm gonna do is, so on ET3 on leaf 2, okay, I'm not going to do anything on here. I'm not going to do anything on leaf 1. I'm going to go to leaf 2. I'm going to configure a priority, lower priority than ET3. I'm going to configure a lower priority than ET3. So ET4 will be sending a lower priority here. So this guy will say, hey, ET3, I'm receiving a lower priority. So I will be the root port. Okay, so we'll see that now. Okay, let me go to the CLI again. Okay, now I'm going to say watch diff. Okay, I'm going to go to leaf 2. What I'm going to do is I'm going to say interface Ethernet 4. You can see here right now Ethernet 4 is alternative. Okay, here also Ethernet 4 is alternative. Okay, right now the priority is 128. Okay, now spanning tree port, I would say priority. So I can configure the value between 0 to 240, 0 to 240, and it is in the increments of 16. So what I'm going to do is I'm going to right now ET3 has 128. So I'm going to be configuring a lower than this one. So I'm going to say 112. Let's see. So watch out. Okay, look at leaf 1 ET4. Now as soon as I change the port priority here on leaf 2 ET4, leaf 1 ET4 should become the root port. Watch out for ET4 on leaf 1. So as you can see here, as soon as I change the port priority here, root port ET4 has become the root port because now ET4 is receiving the lower priority than ET3. Now ED interface ED3, Ethernet 3 on leaf 2, what I'm going to do is I'm going to configure a lower priority than ED4. I'm going to say now 96. Now ED3 should become the root. Yeah. Now you can see that. So if the root path cost is a tiebreaker, then the next deciding factor is the port ID. Whoever receives the lower port ID or the lowest port ID or the best port ID will become the root port. Okay. So this is the second use case is completed. So let me remove the configuration. I'll just make it default. Okay. So I have made it default here. So this is done. Let me go here and this one show active. So let me remove the cost here as well. Okay, so okay, so now I have rebooted everything. Okay, I have rebooted everything. Arch diff. So right now I have rebooted everything. Now ED3 and 4 has become the designated and ED1 become the root bridge. Sorry, root port. Okay. So now next test case will be designated port election, or we can say selection. So how designated ports are elected? So designated ports are elected per segment, per L2 segment. Okay, let me go to the topology back. So if you ask me how many L2 segments I have in this lab setup, I have 4 L2 segments. Okay, 1, 2, 3, 4. So this has already become the root. So we are not going to include that for a designated. So this is uh, the root as well, because we already have a designated here, ED1 and ED2 are designated here. So already elected, designated, and the root already there for these two segments. So these two segments, we are not going to do anything right now. So we are going to be only focusing on the other two segments, which is this segment and this segment. So the election will be per segment. So there will be an election between ED3 and ED3, election between ED4 and ED4. So that's how it is. So the election is between these two guys. So it is within the segment. So one port, one side should become the designated, the other side should become the alternative, because both sides cannot be designated. It has to be, if one side is designated, the other side has to be either alternative or root. Okay, if both sides are designated, then it will create a loop. So that also we'll be seeing both sides as a designated, and loops also we'll be seeing that. I have test cases for that as well. So what I'm going to do is, so right now, the election again, the first is based on the, so whichever, so it is like the election is between ED3, leaf 1 ED3 and leaf 2 ED3. So whoever has the best BPDU, so best BPDU is nothing but the BPDU is the lowest root path cost, lowest bridge ID, lowest MAC address, then lowest port ID. Okay, all these factors. So whoever has the lowest, they'll become the designated. The other side will become alternative. Okay, so these are the things. So the first would be root path cost, second is bridge ID, then the third is the MAC address, and the fourth is the port ID. Okay, so what I'm going to do is I'm going to test all these. MAC address, we cannot test it. We cannot change the MAC address. Okay, so I'm going to be changing the root path cost. Then I'm going to be changing the bridge ID by configuring a different priority, and also I'll be doing the port ID as well by changing the port priority. Okay, so first, what I'm going to do is right now these guys are the designated, because if you look now, right now both leaves have the same root path cost, 20,000. 20,000, it's the same on both. So it's a tie-up. So the next is the priority. The priority is also the same. So the next is the MAC address. So since leaf 1 has lower MAC address than leaf 2, so what happens? Leaf this ED3 telling this guy that Okay, I have this root path cost. What is yours? Okay, we have the same. Okay, I have this bridge ID. What is yours? Okay, we have the same. This is my MAC address. I have this MAC address. What is yours? Yours is that. Okay, I have lower MAC address. So I'm going to become the designated port, and you have to become the alternative port. So that is what happening right now. Okay, but what I'm going to do is I'm going to change that now. Okay, so I'm going to go to. So what I'm going to do is, so right now, if you look at the cost, show spanning tree. Let me do that again. If you look at the cost, let's compare the. Let's only focus on leaf 1 and 2. Okay, let's not focus on spine at the moment. So if you compare the cost, if you compare the cost 20,000, if you compare the cost here 20,000, so both leaves have the root cost of 20,000. So there is a tie. Next is the bridge ID. So both switches have the same bridge ID. Okay, so again a tie up. Now MAC address, if you look at the MAC address of the leaf 1, which is lower, so then leaf 2, so leaf 1, the ED3 on leaf 1 became the designated, both ED3 and ED4. And the port IDs are same. Both sides have the same port ID because I'm using the same interfaces. And the priority is also same, a default priority. So first case, what I'm going to do is I'm going to change the root path cost on the leaf 1 so that ED3 and ED4 should become the designated, because basically we want ED3 and ED4 to lose the election. Okay, so we already, when we were configuring the, when we were doing the root port election manipulation, we already done the same thing. So anyway, I'll do it again. So on ED1, so I'm already on ED1. So interface Ethernet 1. So I'm going to say spanning tree. I'm going to say, I would say, so cost. So now this is the root port. So right now ED1 is the root port. So I have to make changes here. Okay. Okay. So so right now, so I'm not gonna. So ET1. So what I'm gonna do is I'm gonna make ET1 as a root port. I'm not gonna make other ports as a root port. I still want ET1 to be the root port, but I want ET3 and ET4 to lose the election. Okay. So I'm gonna configure the cost of 30,000, because 30,000 is lower than 40,000, because ET3 and 4 have the root path cost of 40,000. If I configure lower than that here, higher than that here, then ET3 will become the root port. So I don't want that, because our test case is completely different. We are focusing on designated, not root port. So now watch out for leaf 2 change. So look at the leaf 2 CLI. So as soon as I change here, there will be a spanning tree reconvergence on leaf 2. Now I'm entering. So now you can see Ethernet 3 and 4 have become the designated. Let me see. Let me show you what is happening right now. Okay. Right now, if you see here, okay, if you see here, if you look at the cost, compare the cost of both. Okay. If you look at the cost of leaf 2, it's 20,000. But the cost of the ED1 is still the root port. ED1 is still the root port, so we are not changing that. Okay. Okay. So, but the root path cost is higher than ET. Sorry, it's higher than leaf 2. Let me go to the topology and explain now. So first deciding factor, I told you, it is root path cost. So ET3 here sends a root path cost of 30,000, and this guy sends a root path cost of 20,000. So this guy says, boss, I have lower path cost, so I will become the designated. This guy sends 20,000, and this guy sends 30,000, and this guy says, boss, I have 30,000. Sorry, I have 20,000. You have 30,000. So I'm the winner. So that's what happening here now. Okay. So let me go back to the lab CLI. So now what I'm going to do is I'm going to remove this. I'm going to now spanning tree. So now I remove that. So now it is default 20,000. Okay. So now it is 20,000. Okay. Now both leaf 1 and 2 have the same root path cost. So the next deciding factor, the bridge ID. So what I'm going to do is bridge ID. I'm going to I'm going to now show watch diff show spanning tree. So now I'm going to make the change on the leaf 2. Okay, right now ED3 and ED4 on leaf 1 are designated because again the default is MAC address. So next what I'm going to do is I'm going to manipulate the bridge ID. So now I cannot change the bridge ID, but I can change the priority. So watch out for the leaf 1, ED3 and ED4 change. So now ED3 and ED4 on leaf 1 should become alternative. So spanning tree priority. So I'm going to configure something like 16,384 something. Or I can just configure secondary something like that. I can do that. So it will configure the automatically it will take the priority 16,000 something. So so I'm going to configure just the priority here 16,003. I hope it is correct. So watch out for the change in the if one. Now if you look at ED3 and ED4 has become alternative. Let me go show you the show spanning tree. Now you look here. So both leaf 1 and 2 have the same root path cost. The next deciding factor is the priority. And if you look at the priority, leaf 2 has lower priority. So ED1, ED3 and 4 has become designated. Now let me go to the topology again. Now what is happening is, let me explain. So this guy is sending the path cost, root path cost, same, both guys are sending the same root path cost, so tie. So then says, okay, we have the same root path cost. Next I'm sending my bridge ID. This guy sends a bridge ID, which is 30,000 something, 32,000. Then this guy sends a bridge ID, 16,000. Then this guy says, hey boss, I have 16,000. My bridge ID is 16,000 something. So mine is lower than yours. So I'm the designated. Then this guy will become alternative. So the same is also happening between ET4 and ET4. So both are sending the same root path cost. Then this is okay. We have the same root path cost. Then they are exchanging the bridge ID. And leaf 2 ET4 says, hey boss, I have lower bridge ID. So that is what happening now. So next, so this is done. So the next what I'm going to do is I'm going to undo this. I'm going to undo this one. Okay, now again ED4, ED3 and ED4 on leaf 1 become the designated. So the next one, what I'm going to do is I'm going to change the port priority on ED3 and ED4. We'll see that. So I'm not confident. I'm not sure about it. Anyway, let me see. Even I haven't tried it yet. So let me try. So spanning tree. Uh, so ED3 and ED4, I'm going to configure the port priority. Uh, right now, leaf 1, the priority is 128. So I'm going to configure 112. Okay, even with the port ID configured, it's not changing. So port ID doesn't matter. So it's the root path cost and the bridge ID, then MAC address, not the port ID. Okay, even I configured a lower port ID, so they are not becoming that. So it's successful now. So port ID is not the factor in the designated port election. So it came into play in the root port election. The root port, we were able to see that, but the designated port. So you're not seeing that. Okay, now what I'm going to do is next. So alternative, so because if one side is designated, the other side has to be either root or alternative. So since root port is already elected, then or the other should become either designated or alternative in this segment. So there is no need to, look at the alternative ports, because the left, whatever is left, whoever loses the election, they will become the alternative port, and they will be discarding. You can see that alternative port will be discarding. So show spanning tree. Okay. So the next use case would be, I'm going to configure root guard. Okay. So right now, let's see. Right now, let me go to spine. On the spine, let me remove the spanning tree root, and let's say super. I removed super here. So what I'm going to do is a spanning tree root. I'm going to configure it as a primary. So spanning tree. Okay. So still the spine is the root. Okay. Okay. This is still the root. Now spanning tree root super. Okay. Hmm. Spanning tree, spanning tree root primary. Okay. Now spine is the okay. Now spine is the root bridge of this network. The priority is 8,000 something. So what I'm going to do is I'm going to configure root guard on all both ED1 and ED2. So interface ET1/ET2 spanning tree guard root. So I enabled spanning tree root guard on spine on both interfaces. Okay. Right now I've enabled root guard on the spine, both ED1 and ED2. What I'm going to do right now is, so right now the priority is 8,000 on the spine. So what I'm going to do is on leaf 2, I'm going to sudo, what I'm going to do is spanning tree root, I'm going to configure what I'm going to do is spanning tree priority 4096. So I'm going to configure a lower priority on leaf 2. So on leaf 2, I'm going to configure a lower priority. So 4096, which is lower than the spine. Okay. So now what should happen is, now we'll see. I'm not going to say what will happen. We'll see what is going to happen. Okay. So spanning tree priority 4096. I'm going to configure it on the leaf 2. Configure it. Now, if you look at the spine, spanning tree has converged. Look at the spine. Now I have two root bridges. Right now, both the spine as well as the leaf 2. They are both climbing to be the root of this fabric. And uh, leaf 1 is also acknowledging that leaf 2 is the root of this network. But what our spine is doing, spine is, if you see, ED1 is connected to leaf 1 and ED2 is connected to leaf 2. So now it is now the role is designated, but it is discarding. The reason is, if you see here, root inconsistent. If you see here, it says root inconsistent. So what happens when I configure the root card on the root bridge? So root cards are supposed to be configured on the root bridges, on the interfaces, on the P2P interfaces, which are point-to-point interfaces. So on the root bridge, we have to configure the root guard on the P2P interfaces. So what happens if some other switch sends a better BPDU? Okay, better BPDU saying that I am the root of this fabric. Then what our actual root will do is, it will put the interface in a discarding state. Okay, it will put that interface in a root inconsistent state. We can see that clearly. It is discarded, designated discarding, and we can see root inconsistent, which means somebody else is claiming to be the root of this network. So interface status also we'll see. Okay, if you look at the interface status, it's still showing connected. Okay, interface, it's still showing connected, but show spanning tree shows clearly that it's discarding, and the reason is root inconsistent. So somebody else is claiming to be the root. So what I'm going to do is, I'm going to remove that now. So now we can see spine. Now it's forwarding. Now it is transitioned from root inconsistent to forwarding state. Okay. So now you would have understood the root guard, why root guard is being used. Okay. So I'm not going to drag much into this. So next I'm going to do a BPDU guard. So root guard we have completed. Next I'm going to configure BPDU guard. So on the spine, I'm going to do that on the spine itself. So root BPDU guards are supposed to be configured on the edge ports. The edge ports are interfaces which are connected to the endpoints, servers, hosts. So so BPDU filter is supposed to be configured on those interfaces. But I'm going to show you what happens if somebody configures BPDU guard on the P2P interfaces. So P2P interfaces are interfaces which are connected to other switches. So these are switch to switch connectivity. If somebody configures BPDU filter here, I'm going to show you what's going to happen. So on the spine, E2, ED1 and 2, I'm going to configure spanning tree guard BPDU. Sorry, spanning tree BPDU guard enable. So let me watch diff show spanning tree. So look at the leaf 1 and 2. So I'm not going to say what is going to happen. So uh, look at leaf 1 and 2. So how spanning tree is converging. So now I'm going to configure BPDU guard here. Okay. So ED1 and 2, I configured BPDU guard. Now spanning tree BPDU guard. Okay, interface Ethernet 1/2 show active. Sorry, I forgot to remove the root guard. No spanning tree. So I enabled spanning tree BPDU guard on the spine. Show spanning tree. Interface at 1/2. show spanning tree. Okay, now let me do it again. 1 and 2, spanning tree, BPDU, card enable. So now I have enabled BPDU guard on Ethernet 1 and 2 on the spine. We'll see what is happening now. Just a minute. I think I understood what is happening. I have to shut down the interface and now shut, because before the interface was shut, now shut. Now, if you see here, uh, interface Ethernet 1/2 and 2, show active. So now show spanning tree. If you see here, I enabled BPDU guard on ET1 and 2. Right now, what is happening is leaf 1 is claiming to be the root bridge, and the spine is claiming to be the root bridge. Spine is claiming that I am the root bridge, and nobody else is acknowledging the spine as the root bridge. The reason is, so what is happening right now is, let me show you, show interface status. If you see here, if you see here, the interface status, it's showing error disabled. So the reason is because I enabled BPDO guard on ET1 and 2. So what happens this BPDO guard? So when an interface, okay, Ethernet 1 and 2 has BPDU guard enabled, what happens? If these interfaces receive any BPDUs, if they receive any BPDUs, then they will go into error disabled state. Okay. So right now what is happening is spine is completely isolated from the fabric. So that's why leaf 1 and leaf 2 are claiming to be the, so leaf 1 and leaf 2 are not aware of spine. If you see Ethernet 1 and Ethernet 1 on both leaves are not showing in the spanning tree output. So because I have enabled show BPDU guard on the spine, it is discarding. What is happening is, if it is receives any BPDUs, it will put that interface in an error disabled state. So interface Ethernet 2, Ethernet 1 and 2, I will say show active, no spanning tree, BPDU guard enable. So now I removed a spanning tree BPDU guard. Okay, so from the interfaces. Now what I'm going to do is, still the interfaces are not up. It's still in error disabled state. Okay, then interface, I will have to now go to ET1 and ET2. I'll have to shut and no shut. Now you can see spanning tree is converging. Now show spanning tree. Now spine is the root bridge again. So BPDU guard, it protects against, you know, spanning tree attacks. Okay, so BPDU guards are recommended, are supposed to be configured on the edge ports where we'll connect the endpoints, because endpoints are not supposed to be participating in this spanning tree. So if somebody sends BPDU on a port which is BPDU guard enabled, STB will put that interface in an error disabled state. So that's what we saw here on the spine. Okay. So what I'm going to do next is, so we saw the root guard, BPDU guard. Next, I'm going to show you the loop guard. Watch diff show. So what I'm going to do is, so loop guard, uh, I'm going to configure loop guard on leaf 2, because loop guards are supposed to be, let's say, are typically configured on the root port on alternative ports. So since I have alternative ports and root port on leaf 2, I'm going to configure the loop guard there on leaf 2, because it has both root port as well as alternative port. So instead of going to each interface, I'm going to configure it on the I'm going to configure it on the global spanning tree guard loop. I think, okay, incomplete command, enable, sorry, default. So I configured a spanning tree loop guard on the global level. So now what I'm going to do is watch diff show spanning tree. Okay, so I enabled spanning tree loop guard on all the interfaces, on the leaf 2. So what I'm going to do is I'm going to go to the uh, the leaf 1. I'm going to go to the leaf 1. So we'll be doing both as well. We'll be doing actually 2 test cases here. One is BPDU filter and loop guard. So we'll be also see what BPDU filter does. Okay. Yeah, as the name suggests, it will just filter BPDUs. So interface Ethernet 3 and 4. 3 and 4 is connected. Okay. So let me explain what happens. So let me explain. So let's say I have not enabled loop guard. Let's say I'm not enabled to loop guard on leaf 2. Okay. Let me do that. Instead of telling you, I'm gonna just I'm gonna so what I'm gonna do is I'm gonna first let me show you the BPDU filter. What BPDU filter does. So on leaf 2, okay, on leaf 1, I'm going to configure BPDU filter on ET3 and ET4. Okay. So okay, spanning tree BPDU filter enable. So on ET3 and ET4 on leaf 1, I'm enabling spanning tree BPDU filter enabled. Watch out for leaf 2. Leaf 2. Watch out for leaf 2. Yes. If you look here, it show. Now if you look here, ET3, ET4 on both leaf 1 and 2 are designated and forwarding. You see that? So are now both are designated and forwarding. The reason is what happens in HTTP. Let me go to that. So let's say these guys are discarding. Okay, ET1, ET2 are discarding. So they are discarding the data traffic. Okay, they are not discarding any BPDUs. So ED3 and ED4 are designated, which means they will be sending BPDUs. Okay, they'll keep sending BPDUs. So what happens? Let's say ED3 stops sending BPDUs for some reason. Let's say unidirectional link failure. Let's say the TX is failed on ET3 and ET4. Let's say TX is failed. Let's say the cable. Let's say I have a duplex cable. Let's say one of the fibers is is faulty. So what happens now? Uh, ET3 is is not sending any BPDUs. So what happens? ET3 here will this alternative, if it does not receive BPDU for a certain time, it will become forwarding. It will transition to forwarding. Okay, if these guys if the alternative port does not receive BPDU for a certain time, it will transition to forwarding state. Okay, that is the default behavior. That is the default behavior of HTTP. So that is what we are seeing here. Okay, so right now what's happening? I configured a BPDU filter. Okay, when an interface is configured with a BPDU filter, it will not send any BPDU, it will not receive any BPDU. Okay, it's for example, it's very you might some people they confuse with BPDU filter and BPDU guard. So there is a subtle difference between BPDU guard and BPDU filter. If you look at the show interface status, BPDU filter keeps the interface connected. But in the BPDU guard, we saw that the interfaces went to error disabled. Okay, BPDU guard puts that interface, when it receives a BPDU, it puts that interface into error disabled state. But BPDU filter does not do anything. It will simply say that you are sending BPDUs, I don't care. I'm not going to send any BPDUs. Even if you send any BPDUs, I'm not going to respond. I'm going to just be idle. I will not do anything. Simply, there is a punch dialogue. Do nothing, eat 5-star. You can just recall that for this. So BPDU filter will be just simply sitting, do nothing. Okay. So that is what happening here. So right now, ED3 and ED4 on leaf 2 are configured with BPD filter. So they are now, say, they are not sending any BPDUs, nor accepting any BPDUs. Okay, so what happens? So naturally, on the other side, the alternative ports came to forwarding, and they are forwarding now. So now it has created a loop. Now it has created a loop. So BPD filters are supposed to be configured on the edge ports, similar to port fast, BPDU guard, and BPDU filter. So all these three are supposed to be configured on the edge ports. So we have to be careful when configuring BPDU filter. So BPDU filter we understood. So what BPDU filter does? So it simply says it's not responding nor accepting any BPDUs. So that the interface is still designated and forwarding, and the other side is also designated and forwarding, and as it has created a loop. Right now, there is a loop. Right now, in this topology, these guys are designated forwarding, these guys are designated forwarding, and I have two routes. Now it has created a loop. It has created a loop. So we have to be careful when configuring the BPD filter. So let me now go to the next test case, which is the loop guard. Okay, so now let me what I'm going to do is I'm going to just a minute. This is a C lab. Let me kill this terminal and create a new one. This is not working. Okay. Let me kill this. So sometimes this happens in the container lab. So what I'm going to do is configure interface Ethernet 3 and 4. So active. So now let me remove the spanning tree PPDU filter enable. So let me first bring it to the default settings. So here also, right now, okay, so spanning tree. So loop guard is not enabled right now. So what I'm going to do now is, okay, so I'm going to enable spanning tree guard loop default. So on spine, on leaf 2, I'm enabling loop guard. So loop guard is enabled. So let me do the watch different command. So loop guard I enabled on the, now before uh, we tested the BPDU filter with the loop guard disabled on the leaf 2. Now I enabled to loop guard on the leaf on leaf 2. Now I'm going to go to interface Ethernet 3 and 4. Okay, interface Ethernet 3 and 4. So now I'm going to say spanning tree BPDU filter. Okay, so what I'm going to do is I'm going to say enable. So as soon as I enable BPDU filter here, ED3 and 4 will stop sending BPDUs and will not accept any BPDU from the peers as well. So I'm just what I'm saying. I'm just simulating that unidirectional link failure scenario here. Okay, so I'm just replicating that, trying to replicate that using BPDU filter. So I'm just trying to replicate that scenario here. So don't try it in an actual network. Okay, so BPD filter I'm enabling. Let's see what happens on leaf 2. Now BPD filter is enabled. Now if you look at the subtle difference, okay, if you look at the subtle difference, so spanning tree. Okay, so without BPDU, without loop guard, what was happening? Both sides were designated and forwarding. But if you look here carefully, it is designated and discarding. And if you can see, it's loop inconsistent state. Okay, so what happens is, so now spanning tree has detected a loop because there was a loop when I configured just BPD filter without a loop guard in the previous test case, it created a loop. Now with the loop guard enabled, now spanning tree has identified that loop. Now what is it doing is it discarding right now. It has put ET3 and ET4 as discarding, and the state is loop inconsistent state. And if you can see here, this guy is still forwarding. ET, ET3 and ET4 on leaf 1 is still forwarding data traffic, because they're not sending BPDUs and receiving BPDUs, but they're still sending data traffic. Okay, so 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 what we are doing is we are right now discarding on leaf 2. So let me see how the show interface status. So the interface status is still connected. It's still showing connected, but the spanning tree is discarding. The spanning tree is discarding now. So now this test case is also done. So next is port fast. So port fast is very simple. So port fast are supposed to be configured on the edge interfaces, interface Ethernet 3, which is the let's say which is the interface which is connected to the server. Spanning tree port fast. You can see that there is a warning. Port fast should only be enabled on ports connected to a single host, connecting hubs, concentration switches, etc. to this interface when fast is enabled can cause temporary bridge loops. So there is a warning. So this port fast, because what happens when we configured an interface as a in a port fast, what will happen is when a switch boots up, okay, because when we power on the switch, it will boot up. So when the switch boots up, so after the boot up, what it will do is the spanning tree will start converging. So it will have to go for listening state, forwarding state, all these states it has to transition. But when an interface is enabled with port fast, it will not go to those transition, listening, forwarding. It will directly go to the forwarding state. It will not go to listening, or it will not be go to listening state. It will directly go to, as soon as it boots up, the interface is boots up, it will directly go to the forwarding. So it might cause a temporary loop if any P2P interfaces are configured with port fast. So we have to be careful on that. So this is a virtual lab, so I cannot reboot any interface. Like, so I cannot do that. But what I can do is, let me do something like this. So let me do interface Ethernet 1. First, let me remove the configuration here. BPD filter. Okay. I disabled BPD filter, interface Ethernet 1, spanning tree, port fast. So port fast is enabled here. Watch def. Okay. Let me remove the loop guard as well. So I have many test cases available pending as well. We'll be doing those test cases as well. So let me do something here. Watch. Okay. Right now on configured port fast, you can see that. You can see that here. Port fast is configured on ET3. Sorry, ET2. On leaf 2, I can see that. Where is leaf 1? Did I configure ET1? Yes, yes, configured. Okay. Okay, spanning tree is using. Okay. So right now what I'm going to do is I'm going to go to the server. So config interface ET1 slash 2 sorry 1.2. So I'm going to shut this down. So let me go back to the topology again. So now you can see that ET2 is actually removed from spanning tree. Okay. So it should be better if I put this, merge this, split two. Let me see. So this one, this. Okay, right now, what I will do is I will quickly go to server and unshut and we'll come here. Okay, we'll see how fast ET2 is coming to forwarding state. Okay, so I'll give no shut. So let me go here. So now I'll enter and quickly go to the leaves and we'll see how fast it is coming to the forwarding state, especially ET2 on both leaves. Okay, enter. Wait, you can see ET2 designated and yep, you can see this ET2 port fast configured comes, it has come to designated forwarding immediately. On leaf 2, we can see that in leaf 2, it is immediately come to okay. So leaf 1, because it's a virtual lab, so sometimes the configurations won't work. Sometimes, let me see. Oh, sorry, I enabled port fast on ET1. My bad, my bad. My bad. I shouldn't have done that. So no spanning tree port fast. My bad. It was my error. So I configured spanning tree port fast on the wrong interface. Okay. So now that's why it's not show spanning tree. Yeah. Right now. Yeah. Let me do the watch as well. Yep. Yep. Right now we can see that. Now we can see that ET2. ET2 is now, because before we were seeing that discarding, right? So this is also good, because the previous one, instead of configuring port fast on ET1, I configured it on instead of ET2, I configured it on ET1. But we were clearly seeing that ET2 on ET2 on leaf 2 became forwarding immediately, came to forwarding immediately. But ET2 on leaf 1 took some time. We were able to see that. Okay. So now let me go back to the server and shut it down. Okay. So right now ET2 is removed. ET2 is removed, and now let me go to the server. Let me go to the server. Now I'm going to give no chat. No chat. I'll click no chat immediately and go to the leaves. Click go. Now if you see, immediately they are coming to forwarding state. So immediately they are coming to forwarding state. Both ET2 on leaf 1 and 2 are immediately coming to forwarding state. There's no delay. Okay, so next test case, what I'm going to do is I'm going to configuring different spanning tree instances. I'm going to be configuring RSTP and rapid PVST. All these I'm going to be doing. So it's 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 taking longer than expected. So bear with me. So we'll do that. I'll quickly. Even I'm also running out of time here. So let me quickly do that. So right now, spine is running. All the switches are running spanning tree. So let me do the watch command again. So let me go to the show spanning tree on the spine. So right now, if you see, all the switches are running MSTP. You can see that clearly here. MSTP, MSTP, MSTP. So now I'm going to configure RSTP on the spine. The spine will be running RSTP and the leaves will be running MSTP. So spanning tree mode, I can say. So Arista supports RSTP, rapid PVST, and backup mode. So we are gonna spanning tree none will disable spanning tree. So backup mode we are not gonna add. We are not gonna see that in this video. So I will be I will be adding about I'll be writing about backup, spanning tree backup in my blog. You can read it there. So spanning tree mode, I'm gonna say RSTP. So configuring RSTP. Now, if you look at spine 1 and sorry, look at leaf 1 and 2. Now, if you look carefully, yeah, spanning tree converged. Yeah, we can clearly see that. Spanning tree has converged. We can clearly see that. Okay, we can clearly see that. But let me show you. So we can clearly see that. So spanning tree has converged. And if you see that, spine is running RSTP right now. And the root bridge is still the spine. The spine is still the root bridge. So leaf 1 and 2 are still acknowledging that the spine is the root bridge. Okay, even though it is running a different STP instance, or let's say a different STP version, I would say that's the right way to say. So it is running a different STP version. So, but there is a subtle difference. If you look carefully, there is a subtle difference. If you look Ethernet 1, now Ethernet 1 has become the boundary. You can see that both are P2P boundary. So boundary means it is connected to, that interface is connected to an STP instance, which is running a different version, which is running RSTP or some other version of STP. So it's a boundary. So ED1 on both leaves are boundary. And another subtle difference is that ET1 on leaf 2 is alternative, and ET1 on leaf 1 is the root. So before, when all the switches were running MSTP, we had one root port per switch per non-root bridge. Now we have only one root port for the, sorry, we still have one root port per root bridge. I beg your pardon. Okay, we still have one root port per switch, but there is a subtle difference here. You can see that ET1, even though it's directly connected to the spine, is not the root port. It is, uh, but whereas ET3 has become the root port. So you might be asking this, why ET3 is the root port, not ET1? Okay, so let's look at the cost. Okay, if you look at the cost on ET1 and ET2, the cost to reach, okay, the cost to reach the root bridge is 20,000 here. Here, 20 plus 20, 40,000. Okay, so let me tell you what is the reason. Okay, so we can see that both leaf 1 and 2 have the same bridge ID, but there is a subtle difference. ET1 has, sorry, leaf 1 has lower MAC address. Leaf 1 has lower MAC address. So what I'm going to do is spanning tree root. I'm going to say secondary, or let me configure priority. So right now leaf 1, the priority is 32,000. So I'm going to configure a lower priority here. Okay, the lower priority is 16,384. So yes, we can clearly see that. So the reason was the election. So between both, because both now are directly connected to the spine. So since leaf 1 has the better, let's say better MAC address, let's lower MAC address, so it became the, so the ED1 on leaf 1 became the root. Now if you look at the priority, ED, uh, this guy ED, leaf 2 has better priority than leaf 1. So ED1 on this leaf 2 has become the root. Okay, so let me do one more thing as well. So let me do one more thing. So right now ET1 here is low. So what I'm going to do is interface Ethernet 1. So spanning tree cost, I'm going to say 10,000. We'll see what is happening now. Okay, now the cost. Okay, now this guy has 10,000 cost, and this guy has 10,000 plus 20,000. Okay, this guy has 20,000 external. This guy has 10,000 external claw. So the tiebreaker, the comparison. So both leaf 1 and 2 have the external cost. Right now, leaf 1 uh, leaf 1 has the 10,000 external cost. The internal cost is 0 because it's directly connected. This internal cost is the cost between leaf 1 and 2, that is 20,000. Okay, so right now this guy has 20,000 cost, this guy has 10,000 cost, so this guy won. So then if the cost are same, if both leaf 1 and 2 have the same cost, then the next deciding factor is the priority. We were able to see that because I configured a lower priority on leaf 2. So then ET1 on the leaf 2 became the root port. Then if both are tie, both cost as well as both priority or bridge ID are tie, then whoever has the lowest MAC address, then the interface on that will become the root port, especially when they are directly connected. Okay, we were able to see this. So this is good. Now what I'm going to do is I'm going to configure a different, let's say I'm going to configure spanning tree mode rapid PVST. So now on the spine I'm going to run rapid PVST. Then we'll see what is the what's diff. So now I'm going to change the uh, RSTP to rapid PVST on the spine. Okay, let me see. So now spanning tree is converging now. So now we can clearly see that now spanning tree is converging. Now leaf 2 has become the root. If you see here, spine is also climbing to be the root for all VLANs. It has three VLANs, VLAN 1, VLAN 10, VLAN 20. For all three VLANs, spine is climbing to be the root. And if you see, leaf 1 is climbing to be the root. And here, leaf 2 is claiming to be the root, and leaf 1 is only acknowledging leaf 2. So both leaf 1 and 2 don't recognize the spine. Now, so if I go to spine, and you can see the one, if you look at the bridge ID, now you are seeing a different bridge ID. You can see that sys ID and 1 plus 1 here plus 10 here plus 20. So the bridge ID is the combination of priority, system ID, and the STP instance ID. Okay, so right now let me show you one more thing. Show interface status. And if you see here on the spine, both ET1 and 2 are in error disabled state because it's not recognizing MSTP. Okay, so rapid PVST we have tested. Okay, so rapid PVST. Now let me do one more thing. On the leaf 2, I'm going to run spanning tree mode. I'm going to say RSTP here. So let me do that. So right now, all three switches are running different STP instances, different STP versions. Leaf 1 is running RSTP, spine is running rapid PVST, and the leaf 2 is running MSTP. But still, leaf 2 is the root bridge for still leaf 1, even though it is running RSTP, it's recognizing leaf 2 as the root bridge, but none of them recognizes spine. And spines Ethernet 1 and 2 are in error disabled state right now. Okay, let me reword everything. Now I'm going to quickly test the failure scenario. Okay, spanning tree mode MSTP. Okay, so and I have to interface Ethernet 1 and 2. I have to shut and no shut. So now so now the spine has become the root because now let me also do that here. Spanning tree mode, I'm going to run MSTP. So what I'm going to do is I'm not going to do show. Okay, so on the spine, we'll be seeing the MAC address table. We'll be monitoring the MAC address table changes on the spine. So on the on the leaf 2 as well. Show, sorry, watch. Okay, so let me go to this. Okay, right now. So what I'm going to do is I'm going to start the ping bit from the server. Oh, shit. So I'm going to say ping 192.168.10.254. So this is the gateway for VLAN 10. So I'm going to repeat. I'm going to do this 100 times interval and I'm going to say every 1 second. So pings are going. Okay, so let me go to the leaf one. Show spanning tree. So what I'm going to do is now I'm going to shut down the ET1. So let me see the MAC address table. If you see here, right now the spine is learning about this on ET1. Okay, right now the spine is learning about this MAC address on ET1, and leaf 2 is also learning about this on ET1. So both are learning this MAC address through ET1. So interface ET1. So on leaf 1, I'm going to shut down ET1. Now we'll see how fast the MAC address table is moving. I'm going to say shut down. Now the MAC address table is immediately changing. Okay, we can see that now from 1 to 2 it's changed, and here also we can see that from it is moved to ET3. Now it is going to ET3 right now. So now interface ET3. Now I shut down that. So ET3 is shut down. Now it is moved to ET4. Now on here it's moved to ET4. Okay, now it's moved to ET4. Now what I'm going to do is I cannot shut down all the interfaces. Then nothing, no shutdown. So now it will again change to ET3. Yes, spanning tree is converging. Interface ET. I think the ping has stopped. Yep. So we can see about 2% packet loss, which means 2 ping drops. We saw 2 ping drops here. Okay. So spanning tree convergence is fast. Spanning tree convergence is very fast here. Let me do it uh, let me do it from other VLAN 20 as well this time quickly. So ET interface ET1 shut. Okay. So now what I'm going to do is watch diff show MAC address. So now I'm going to be pinging from VLAN 20. Start ping. So pings are going now. Okay. So now let me go here, and I can see that right now it is receiving this from ET2, Ethernet 2, and the spine is receiving it from Ethernet. Show MAC address table. So right now it is actually going through leaf 2. You can see that ET2 right now, ET2 and ET1. It's going through ET2 and ET1. So this is the MAC address of the 46 is the spine MAC address. This 1439 is the leaf's MAC address. So what I'm going to do is I'm going to shut down ET1. Okay. So right now the spine is receiving this traffic from through ET1. Okay, sorry, ET2. Okay. So now I'm going to shut this down. So now it's quickly changing. If you can see that, so spine is quickly changing this from ET2 to ET1. So now uh, leaf 1 is receiving it via ET3, Ethernet 3. So now interface Ethernet 3, I'm going to shut down as well. Now it should be receiving it by ET4. Now it's quickly changing to ET4 now. So that's how fast now spanning tree is transitioning nowadays. So this is the leaf spine fabric. So because depending on the network size, the latency might vary. Okay. So depending on your L2 fabric size, the latency might vary. And also, this is the leaf spine architecture that it's a very simple lab setup. So that's why it is very fast. But depending on your L2 fabric size, this timing might vary. Here also I can see 2% packet loss, which is like 2 ping drops. You can see. So so I hope this video was really helpful. So uh, you can read my blog. I will also attach this link video in my blog as well. So so thanks for watching the video. If you have any questions or queries, you can uh, you can put it in the comment section. I'll be addressing your questions there. Yeah. Thanks for watching the video.